Hello everyone, nice to talk to you all. So this class we're going to continue our contents on the fundamentals of environmental engineering and science. In this class we're going to basically follow up with what we have learned from last class about the water quality management in different types of water resources. And now we just have one thing left, which is the groundwater quality. So in terms of the groundwater quality, we need to consider about different sources of contamination. So if we look at these sources, they might include the improperly operated septic systems, leaking underground storage tanks, and there can be spills, accidents, or other leaking from different types of pollutant sources. And in terms of the water ground quality management, there's one parameter that is quite important, which is called the retardation coefficient. The reason why we're interested in this factor is because most of the contaminants in the water will actually move at the same speed or same rate or slower than the water because of the absorption. Because if we think about the soil components, they're composed of many tiny solids or soil particles, and these contaminants would actually get absorbed at the surface of these particles. And because of that, the moving velocity or the linear velocity of these contaminants will become lower. So that's why we define this retardation coefficient. For example, if the water moves with a speed of 1 millimeter per second, while the contaminant moves with a speed of 0.1 millimeter per second, then the retardation coefficient is calculated by 1 divided by 0.1, which is equal to 10. So as you can see, the higher the retardation coefficient, then the lower or the slower the speed of these contaminants. All right, we can do a quick example or quick practice of how this might affect the groundwater quality. So for example, we are neighbors, right? For example, if we live close to each other and I decided to dump some chemicals into the groundwater, okay, and these chemicals are basically leaked from my, for example, septic tank, okay. So the distance between these two houses, let's say it's 60 meters, and the linear velocity of water is 4.7 multiplied by 10 to the minus 6 meter per second. So you can see that this speed is actually a very small speed if we consider about the movement of the water underground. And the retardation coefficient is 2.4. So what this means is that the contaminant velocity, so according to the definition of this retardation coefficient, is defined by velocity of water divided by the velocity of the contaminant. So because of that, the velocity of the contaminant will be equal to velocity of water divided by this retardation coefficient, right? So that's going to be 4.7 multiplied by 10 to the minus 6 divided by 2.4. Okay, so this is going to be the velocity of this contaminant. And since we already know the distance between these two houses, then we can calculate what is the time that's required to reach to the second house, right? To reach for these contaminants to reach from the house A to house B, which is equal to 60 meters divided by 4.7 multiplied by 10 to the minus 6 divided by 2.4 meter per second. All right, and you can find out that actually the time is around 354 days. So you can see that the contaminants can really move with a very slow speed from one location to the other, right? 60 meters is not a very long distance. Okay, so that's all about the water quality control or water quality management in different water resources. So if we think back, we first discussed the water quality management in rivers. And specifically, we talk about the BOD, and then we studied the dissolved oxygen sag curve, which is because of the two processes, right? You have the aeration and also the deoxygenation process. All right, and then we talked about briefly go over the water quality control in other different water sources. For example, the lakes, estuaries, oceans, and now we talk about the groundwater. And that's pretty much all for chapter 9. And Today we're going to continue our topic and then study the water treatment. Okay, so here we specifically mean drinking water treatment, and then later we're going to learn about chapter 11, which is about the wastewater treatment. So in terms of the drinking water treatment, to treat the water quality to treat these water quality, we need to first know where are these water coming from, right? So this water might come from very clean sources, for example, from the icebergs, right? We don't even need to do a lot of these treatments. But unfortunately, most of the water that we drink are either from the groundwater, basically from the deep wells, or it can come from the shallow wells, which includes the river, lakes, or reservoirs. Okay, so for the deep wells, which is which is the groundwater in very low depths there, they can be relatively clean, which means that they're free of bacteria or free of debris from all different natural processes, right? It's kind of difficult for these bacteria or virus to live in the groundwater, which is at that very deep location there. But the problem for these deep well water is that they may be very hard. So by meaning hard, we mean that there are a lot of these ion species, for example, calcium, magnesium. So basically those ions that are able to form sediments when they're heated. And specifically, these ions are dissolvable when they combine with the bicarbonate ion. For example, for calcium, so the calcium bicarbonate or magnesium bicarbonate, they're dissolvable, they're soluble in water. But when they're getting heated, they'll turn into solids. For example, calcium carbonate or magnesium carbonate. Okay, and this actually happens quite a lot because quite a lot in Rolla, because most of the drinking water resources from Rolla are actually from the deep wells. Okay, so that's why our water is very hard. So whenever you go to the water fountain, pick up some water, you can even see those sediments in the water, right? And another major source of the drinking water are actually from these rivers, lakes, or reservoirs, or these shallower wells. So for these water, or these water resources, water quality might be might be worse. This is because there can be a lot of pollutants that's coming from the air. They can get dissolved into the water, and then it's also accessible for those bacteria to live in the water, right? So specifically, we talk about the BOD. So the reason why these BOD can happen is because there are a lot of microorganisms to dissolve those organics, right? So while we have to treat those organics or remove those organics from the water, we also need to remove the microorganisms from the water. Okay, so because of that, the water from these shallow wells or rivers or lakes, they will need more treatment. And then once we talk about the sources of the drinking water, then we need to know what is basically a accepted water or potable water, right? We need to know about the water quality concern. So the concerns for these water quality can be in different, in many aspects, okay? So they can be the appearance of the water, for example, include the color, the odor, turbidity, or solids, right? So in your labs, you actually saw the wastewater or river water that the TA brought to the lab session. You can see those waters typically very turbid, has a lot of suspended particles or colloids, right? Sometimes if you smell it, you can smell the odor there. So those are not potable water, right? We have to properly treat these water to convert them into drinkable water. And then there are also a lot of pathogens, bacteria, viruses, and so on and so forth. There are organic pollutants, right? Because these water, they're also subject to the emission or the chemicals that's being released from the industrial plants. There can be inorganic pollutants, for example, heavy metals. And we also need to consider that there are disinfectants. There are disinfectants and disinfection byproducts. And there can also be some radionuclides, which are harmful to the human health too. Okay. And once we know these concerns, there are actually also standards for the water quality. So basically, the EPA established the maximum contaminant level, which is enforceable to regulate these species or substances. And there's also a maximum contaminant level goal, which also applies for can be applied to some of these contaminants in the water. So now if we talk about the treatment methods, as you can imagine, for example, if we're talking about treating the water quality from a river, then you can think of that if we just look at the river water, then there can be a lot of larger particles, larger species, right? Of course, there are fish if the water is very clear. And also there can be some leaves that's floating around at the top of the water. There can be some algae, right? So we want to get rid of these species or these larger particles before they enter the water treatment facility. So basically, for these debris, we'll use the screening method to remove these larger objects. And there also can be some heavy particles. For example, just the soil particles or the sand. And to remove these particles, we can just let it stay still so that they can use their gravity to settle down to the bottom. And then we can further process the water. And there can also be microorganisms. And for these microorganisms, we have to use disinfection. And you had done some lab studies last week, right? And specifically for the disinfection, this wasn't realized until actually the year of 1908. So as we have introduced in the history of the water treatment. Now actually, people noticed that after they started the chlorination, which is basically pumping chlorine into the water and then to remove those microorganisms, then the concentrations of these microorganisms decreased and can be eliminated. And then this can also reduce the death rate for these typhoid fever, right? You can see that the human health is clearly related with the water quality. And there are also more complex methods to get rid of the contaminants in the water. For example, for the colloid or the suspended particles, or suspended solids, because the particles are relatively small, there's no way that they can settle down by their gravity, right? And also for some soluble pollutants, and people will use the coagulation, flocculation, and clarification. So notice that this is a series of treatment, but actually, once one of these happen, the other two have to accompany one of these, accompany the others, right? So this is basically a single step, but it includes three sub-steps, right? And for very small particles, we can further remove them by the sand filtration. And of course, if the water doesn't have a lot of these colloid or suspended solids or soluble pollutants, we can directly push these water through the sand filtration, which means that if the water quality was already pretty acceptable before being treated, we can just use a simple filtration to purify the water. And for the deep well water, which is the major source of potable water in Rolla, we have to consider about the hardness. So basically, we need to remove the hardness from the water. And for this process, we call that as softening, right? You can think of how we can counteract each other, right? So the water is very hard because there are a lot of these metal ions which might form solids when they're getting heated. And then we use the softening method to remove these metal ions before they're distributed into different locations, right? And finally, for those dissolved organic pollutants or odors, we can use the activated carbon adsorption. So basically, these are activated carbon or activated charcoal, which provides a very large surface area. So we have this very large surface area, then these molecules can get attached on the surface, and then we can further regenerate these activated carbon, right, to get rid of these pollutants. So here I'm going to show a schematic diagram of a water treatment facility. So I noticed that your already basically let you know that the water treatment plant tour was canceled because of some management requirements. So because of that, we have to learn about how the water treatment facility works, how this facility works through some videos. Okay, so so for example, here I'm talking about a water treatment plant that's using lake water as the water source. So basically, after they're pumped into the pipes, so first we'll use some screening method, right? To use some protective bar screen or traveling water screen to remove these larger particles or debris from the water. For example, the fish or the leaves, right? And then we'll pump this water into a reservoir. And not typically we'll use these low lift pump wells. So low lift pump consumes less power and they can basically pour more water at a faster flow rate. And so basically we won't need to elevate the altitude or elevate the height of the water by much. So that's why it's not going to consume a lot of power. So after the power injected into these channels, we'll first go through a pre-chlorination to remove some of the microorganisms. So of course, if the water is very clean, we can ignore this step and then do the chlorination at the very end. And then here we will talk about the coagulation, flocculation, and clarification. Okay, so you can see that these three steps are actually related with each other. So here, the clarification, we're using a sedimentation basin, basically to let these larger particles or these flocks to settle down to the very basin, to the very bottom of the basin. Okay. So the method it works is that we'll inject some coagulants, basically some chemical coagulants, and you learn from the lab that we can introduce alum into the water and then to let these alum or aluminum ion to coagulate or the aluminum hydroxide to coagulate with these colloids and then form larger particles. And in the flocculation, we'll kind of stir the water, but we don't want to break these particles or break these larger particles and basically to let them form larger flocks. And then these larger flocks will settle down in the sedimentation basin. And then at the top of this basin here, we'll get relatively cleaner water. And then we can feed these water through the sand filtration. So as I have introduced, if the water quality is already clean enough, we can probably just ignore these previous steps and directly feed them into the sand filtration. But unfortunately, for most of the area, the water treatment, we have to go through these complex water treatment process because the water is not directly potable. Okay, so after the water are treated, they'll go through the basically the post-chlorination to further remove these microorganisms. People also will try to pump in ozone into the water to oxidize those organics or microorganisms. And finally we'll go through this fluoridation process, which basically introduce fluoride into water to protect the teeth of the people, especially for the children. And then these water will basically satisfy the drinkable water requirements, and then they can be used pumped by these high lift pump well, and then we can store them into the storage tower, or store them into the ground level reservoir. Okay, so because of these excess sources of the water, we can distribute them more conveniently into different houses. So as you can see, if we're talking about the treatment of water that are not very clean here, we need to go through a quite complex processes. And the reason why we go through this process also have some logic behind. Okay, so for example, you can imagine why the sand filtration have to be after the coagulation, flocculation, and sedimentation. And this is because if we already put this sand filtration at the beginning, for example at here, then those colloids will also get removed, right? So there's no reason for us to use these coagulation, flocculation methods anymore. But the problem is that The problem is that then the sand filtration might get easily saturated because there can be a lot of colloids in the water, right? And remember that for these coagulation flocculation method, they not only treat these suspended solids or colloid, they can also treat some of these soluble pollutants, for example, some organics or some ions in the water, right? So that's why we want to form those flocks, right, before the sand filtration so that these larger particles or larger flocks can get removed from this sand filtration. Okay? So now we can go into further details about some of the important steps in water treatment. So also notice that since we're treating the quality of the lake water, we don't use the softening step. This is because the hardness of the lake water is typically quite low. But if we're talking about the treatment of the groundwater, typically we need to include the softening step into this water treatment plant. Okay, so here I also have a short video that will introduce you how basically briefly how a water treatment plant will work. So we can briefly go through this video for now.
Welcome to our tour of Winnipeg's drinking water supply and treatment system. We use leading-edge technology to treat the water as it passes through many stages, including coagulation, flocculation, dissolved air flotation, filtration, and 3 types of disinfection. Our system protects public health by virtually eliminating the risk of waterborne disease and reducing the level of harmful disinfection byproducts. It also improves the taste, odor, and appearance of our tap water. Shoal Lake has been our source of water since 1919. It's located 136 kilometers from Winnipeg at the Manitoba-Ontario border and is approximately 92 meters higher than Winnipeg. Water flows downhill from Shoal Lake through an aqueduct into 4 large reservoirs next to the treatment plant. The aqueduct is a large concrete pipe that carries up to 386 million liters of water per day to the reservoirs. The reservoirs hold up to 8.8 billion liters of water, which on average is enough to supply Winnipeg for about 30 days. Water flows from the reservoirs through 2 large pipes into powerful pumps that move the water into the plant for treatment. This $300 million state-of-the-art facility features a highly automated system that monitors and controls a wide variety of instruments, mechanical equipment, and electrical equipment including 40 processors, 140 pumps, 2,300 valves, and 1,400 instruments. It can treat up to 400 million liters of water per day. In this first step, we add sulfuric acid and ferric chloride as the water flows into the plant. Sulfuric acid lowers the pH of the water and makes this stage of treatment more efficient. Ferric chloride, a coagulant, causes the naturally occurring particles of organic material in the water to attract each other. The water enters flocculation basins, where large mixers slowly stir the water, causing the particles to collide and stick together, creating large clumps. Now that large clumps have been formed in the water, the next step is to remove them. We do this in dissolved air flotation tanks. We inject a stream of water, supersaturated with air, into the flocculated water which is flowing into the bottom of the tanks. Tiny air bubbles are released into the water and carry the clumps to the top of the tanks. Skimmers remove the floating clumps from the surface of the water. The clumps are pumped to an area for further processing. The treated water is collected from the bottom of the tanks. The water flows from the dissolved air flotation tanks to chambers where ozone is added. This step, called ozonation, does 3 things. It provides the first level of disinfection by destroying most of the harmful bacteria. It improves the filter performance in the next treatment stage. And it improves the taste and odor of the water. We make ozone by applying electricity to liquid oxygen. At the end of the ozone chambers, we add sodium bisulfite to the ozonated water to remove any leftover ozone. The water now flows into filter tanks containing biologically activated carbon. The filters remove any remaining small particles in the water, including parasites. Good bacteria growing on the filters remove some of the remaining dissolved organic material. This reduces the level of disinfection byproducts in the water. We clean the filters regularly by pumping air and water backwards through them. The backwashed water is pumped to an area for additional processing. The filtered water flows into the chlorine contact chamber for a second round of disinfection. We add chlorine to kill viruses and bacteria such as E. coli that might be in the water. Chlorine is the most widely used drinking water disinfectant in North America and has been used for more than 100 years. We then add sodium hydroxide to bring back the pH of the water close to the original level. The water flows from the chlorine contact chamber into an underground reservoir called the clear well. We disinfect the water once again using ultraviolet or UV light. We pump the water through 6 stainless steel chambers, each containing 9 ultraviolet lamps. The lamps are similar to fluorescent bulbs. With only seconds of exposure, the UV light rays penetrate any remaining parasites, such as Cryptosporidium or Giardia. The UV light renders these parasites harmless. After UV disinfection, the water flows into 2 large pipes where we add fluoride to help prevent tooth decay. We also add orthophosphate to form a protective coating inside water pipes. This coating helps reduce corrosion that may add lead to tap water. The 2 large pipes carry the treated water to our 3 reservoirs and pumping stations in the city. We add chlorine again as the water is pumped into the distribution system to ensure that the water remains disinfected until it reaches your tap. The final stage of treatment is to deal with the materials removed from the water by the treatment processes. The backwash water from the filters is allowed to stand until the solid materials settle. We then send the clean water back to the beginning of the treatment process. We pump the settled out material from the filters and the clumps of particles from the dissolved air flotation process to outdoor settling ponds next to the treatment plant. The pond contents go through natural freeze-thaw cycles, which separate the liquid and solids. We pump the liquid into Winnipeg's sewer system for wastewater treatment and take the solids to the landfill for disposal. We test our water each step of the way, from Shoal Lake to your tap. Our testing program includes over 150 different tests at more than 130 different locations throughout the year. Because water quality is so important, we do more testing than the provincial government requires. Our certified professional team is dedicated to ensuring that our community enjoys safe, high-quality drinking water that meets provincial regulatory requirements and falls well within Health Canada guidelines. We hope that you've enjoyed this tour of our drinking water supply and treatment system.
All right, so you can see that actually for a real water treatment system, the detailed steps for treating the water quality might be a little bit different, but actually we're going through typically the same mechanism, right, to remove the particles, remove the chemicals, and also remove the microorganisms. So here we'll talk more about how we can remove the colloids, basically, which are the most difficult to remove in the water, right? And as I've mentioned, this process is called the coagulation, flocculation, and clarification. So what it does is it removes the turbidity, color, and bacteria. Okay. So the reason why these colloids, or why the water always shows this turbidity, is actually because there are a lot of very small suspended particles in the water. So particles very small, so because of that, they're not going to be easily settled down into the water. All right. And as a matter of fact, if you just bring the water sample that we took from the wastewater or from the river water, it can keep that color for years. And this is not because the water has that color, right? Because not because of some chemicals that are dissolving into the water. It was because of those very small particles or colloids. They're very stable. First, it is because that they're very small. So the gravity of these particles are relatively small. It's not easy to remove these particles by just sedimentation. And also, this is because that they're negatively charged. So you may wonder why these particles tend to be negatively charged. It is because a lot of these water samples actually carry the soils, right? If we think about what soil or what sand is composed of, they're composed of silicon dioxide, right? So if we further draw the schematics or the structure of the silicon dioxide, they are actually composed of these structures, right? So each of these silicon is surrounded by 4 oxygen, and each of the oxygen is surrounded, basically linked to 2 silicons. So as a matter of fact, so for these clay particles or for these sand particles, they typically tend to exist in such a way, okay? So they're not going to exist in an exact ratio of 1 to 2 in terms of the moles of silicon and oxide. So typically there will always be a little bit more oxygen in these soil particles or sand particles. And because of that, if you think about what is the charging state of the silicon, so silicon here, it carries +4 charge, right? Oxygen, each of the oxygen carries -2 charge. And because of that, it means that there are more negative charge for these soil particles or sand particles. And because all of these very small colloids or small particles carry these negative charge, they repel each other, right? If they carry different charges, they can easily collide with each other, form larger particles. But because of these same charges, they will repel and then coexist in the water. And at the same time, the Brownian motion of these very small particles keep pushing the particles, and then it's not easy for them to collide with each other. So Brownian motion basically means that there are a lot of water molecules in the water, and then if we have a particle here, and then these molecules will collide onto these larger particles, and then the particles will move around. We call this process as the Brownian motion. And the Brownian motion will keep particles basically away from each other, and then they can coexist in the water there. So the method or the material that we put into the water to remove these colloids is called a coagulant. So basically, the coagulant will neutralize the surface charge. So let's say these suspended particles carry negative charges. Then why not we just introduce positively charged ions, right? And specifically for these positively charged ions, the ones that carries +3 charges, or the trivalent ions, are the most effective. So if we think about these +3 charged ions, they can be aluminum ion, right? They can be ferric ion. So once we introduce these ions, they don't have to be, because for any material that we put in the water, they have to be neutral. So for example, for these aluminum, we'll put alum inside. So basically, alum is composed of aluminum sulfate, right? So once they get dissolved into the water, they will form the aluminum hydroxide. And the aluminum hydroxide will tend to carry positive charges. That is because they are mainly affected by these aluminum ions in the water. And then they can start to break down these negatively charged colloids, and then form larger particles. And we call these larger particles as flocks. Okay? And of course, if there are too much coagulants, then this will reverse the charge. For example, it will give all of these colloids positive charges, and then they can start to repel each other again. So we always want to put in the correct amount of these coagulants into the water, and then to remove these colloids. So here, this is basically what I'm showing about the charges on the particle. So typically, this light green particle, or sphere here, represents a particle in the water, and they will carry a net negative charge, right? And then because in the water there are a lot of ions in the water, dissolved ions, and they can first form a single layer surrounding this negatively charged particle. This is directly because of the attraction of different charges, right? And then further, this positive layer, ionic layer, is going to give this entire ensemble a positive charge. And then there can be a second layer surrounding this larger particle here. And this second layer basically will carry more negative charges. So as you can see, for each of the particles in the water, they are composed of two different layers. And this is also the reason why it is difficult to break down these suspended particles and then remove them from the water, right? So here it is showing how the concentration of these ions that we add into the water can affect the turbidity, or affect how effective we can remove these colloids. So you can see that if we can use aluminum ion, right, we typically will use a smaller or lower dosage of the coagulant, and this will reduce the turbidity of the water. If we use calcium ion, typically we'll use a higher concentration of the coagulants, and for sodium ion, it is just wasting a lot of materials in the water, right? We can also use these organic polymers. They can also work to remove these these larger colloids, but the problem is that it is very sensitive to the concentration of these the coagulants. If the concentration is too high, then these flux will get resuspended in the water, and you can see that the turbidity will increase again. Okay. So, as we can see, by introducing these coagulants into the water, we can remove the colloids. But what is really happening here? It has to go through some chemical reactions, right? So for example, if we're introducing the aluminum sulfate into the water, which is also called the alum, so these aluminum sulfate can basically first dissolve these aluminum ion into the water, and because of the pH range, the aluminum ion is going to react with the water to form the aluminum hydroxide. And these will form sediments, so basically they can further interact with the particles in the water, and then they can form larger flux, basically form a larger clumps of water particles. And as you can see, the higher the pH, that will create larger flux, simply because the higher the pH, the more aluminum hydroxide we're going to form from this reaction. We can also introduce ferric sulfate into water. So we can introduce a ferric sulfate or the ferric chloride, basically, to introduce these ferric ions into the water. And similar to the aluminum, they're going to form these ferric hydroxide, and they can also coagulate with the colloids in the water to form those larger flux. So apart from these coagulants, we can also use the coagulant aids. So basically, these are additional ingredients we can put into the water to enhance this coagulation process. For example, we can use it or introduce the activated silica, clay, or some polymers. The reason why we can introduce activated silica or clay is that if you think about the turbidity in the water, they're basically very small suspended particles of the silica, clay, or sand residues, right? So basically, by introducing more of these negatively charged particles, once we form these flux, they can more easily get coagulated with these negatively charged particles, right? Once we form these hydroxide sediments, they're going to form larger flux, and the larger flux will enhance the coagulation process. Basically, you have a larger object, and they can more easily collide with other particles in the water, right? We can also adjust the alkalinity, or basically to adjust the pH. So what it is that basically the higher the alkalinity, or the higher the pH value, the better the coagulation. will happen, right? So as we can see from these two reactions, so basically the coagulation process is going to generate some proton ions, right? So what this means is that basically the water is going to become more acidic as we introduce these coagulant into the water. So more specifically, or a more scientific way to show these reactions is actually these coagulants will react with the alkalinity in the water, which is basically these bicarbonate ions in the water. So basically, these aluminum sulfate will react with the bicarbonate ion to form these aluminum hydroxide, and also they're going to form the carbon dioxide. So as you can see, for this reaction here, they're not necessarily forming the protons, right? So how can we know that the reaction is going to more acidic regime? This is because the coagulant or the coagulation reaction basically consumes the bicarbonate, right? And as we have introduced earlier, bicarbonate should be counted as the alkalinity, right? So the alkalinity is calculated by the bicarbonate ion, right? Plus twice of the carbonic ion, plus OH ion, and then minus the hydrogen ion, right? So by consuming these bicarbonate ion, we're reducing the alkalinity, which means that acidity of the water will enhance, right? So the water will become more acidic. So basically, from this coagulation reaction here, we can also calculate how the alkalinity is being changed if we introduce coagulants into the water. For example, in this example problem on your textbook, it actually wants you to calculate what happens. So basically, what is the total mass of the alkalinity that's being consumed if we introduce certain amount of alum into the water treatment plant, right? So basically, we can calculate how much bicarbonate are being consumed if we use a stoichiometry, and then we can calculate what is the mass of bicarbonate being removed from the water treatment process. Okay, so this is about the coagulation, right? So if we think about this coagulation process, let's say this is our water treatment plant. We introduce this coagulant into the water. So do we want of course, we want to suspend these coagulant into the water, right? So basically, we don't want the water to be flowing and then these coagulants just form these larger rocks and then settle into the bottom, right? We want this coagulant to be fully suspended in the water. So because of that, we're going to use a rapid mixing when the coagulants are introduced into the water. So basically, the rapid mix will guarantee that it will quickly disperse the chemicals to particle surface for surface charge neutralization, right? We're going to use a lot of these propellers or turbines to achieve this rapid mixing of the coagulant and the colloids in there. So a value that can calculate what is the degree of mixing is basically calculated by this velocity gradient. So based on this name, you can actually see how this velocity gradient is calculated, right? So it is just dv divided by dx. So if you think of a propeller here, so basically this is the velocity gradient from the edge of the propeller compared to the inside of the propeller, right? So if we plot the velocity that's along this propeller, we can see that the more distance, or the further away from the center axis, the higher the velocity in there, right? And also because of this calculation, the velocity gradient will carry a unit of per second, right? So basically, for this rapid mixing process, they will achieve a velocity gradient of 700 to 1000 per second. So what this means is that if we can have a turbine, if we design a turbine that has basically a radius of 1 meter, then based on this calculation, you can see that at the edge of the turbine, the velocity is basically 1000 meter per second, right? This is a very high speed that's taking place in the water. and because at the center the water velocity is 0, right? So there's a very rapid mixing taking place in the water. And for these mixing processes, we also will define a parameter called the retention time. Sometimes people will also call that as detention time. So basically, this is a time that the water spends in this reactor here, in this mixer here. Okay, so how does this time affect the design? So basically, for each tank, there will be a flow rate that's associated with the processing, right? So the higher the flow rate, we need the longer. Typically, we need a longer retention time. So basically, to guarantee a better mixing of the water. So this involves the design of the tank or this reactor here. So if we have the retention time of the reactor here, then we can calculate what is the volume. So the volume of the reactor is simply the flow rate that's going into the reactor multiplied by the time or the retention time in there. So for example, if we're talking about this mixing tank having a flow rate of 100 meter cube per second, and then if it has a retention time of 20 seconds, it simply means that the total volume should be 2000 meter cube, right? Okay, so after the rapid mixing, of course, for this rapid mixing, there can be all different types of designs, right? You can use a turbine chamber, propeller chamber, and then you can also design these double stage or compartment, different compartments that's composing this chamber here. Okay, so after the rapid mixing, if we further think about the process that's going to happen, right? So let's say this is our reactor here. We introduced these coagulants into the water, and first we use this turbine to fully suspend these coagulants and then let them get in contact with the colloids, and then we transfer them into another reactor here. Okay, and here we still want some of the mixing because the mixing is still needed to guarantee that the reactor is homogeneous. But let's think about it. So if we talk about the velocity gradient, remember that G value. So is the G2 larger than G1 or smaller than G1? Which means that do we need a higher speed of the turbine in this second tank here, or we need a smaller, we need a lower power of this turbine in here? So basically we need the turbine to rotate slower. This is mainly because once these coagulation will take place, we're going to form these larger flocks, right? For these larger flocks, we don't want to use a very high speed of the turbine because it's very easy to resuspend or break these flocks, and then they can get suspended in the water again, right? We want a slower speed so that they can use their gravity to settle down to the bottom of the chamber there. So because of that, we'll use a slower mixing and allow the particles to further form these larger flocks. And also this slower mixing will avoid the flocks being broken and resuspended. So as we can see, the G value, which is the velocity gradient here, reduces from 1,700 to 1,000 to around 30 to 60, which is relatively smaller. And also the retention time is also getting larger because we need a longer time for the water to settle down in this flocculation chamber. And in terms of the design for the flocculation chamber, we can use the paddle flocculators or the baffled channels. Okay, so these are two different designs for the coagulation chambers. So here, basically, this is showing the paddle flocculators. It is composed of a main shaft, right? You have a lot of these paddles in the chamber here, and they're going to rotate at a relatively slower speed here to enhance or promote the flocculation to take place. And here are also some schematic designs for the flocculators. So for example, for the paddle flocculators, the flocculator can also be installed in the horizontal way, right? And basically these paddles will rotate to facilitate the mixing, and also the speed is slow enough so that the flocks are not being broken, right? And then these larger flux can get settled down to the bottom. And then we also divide them into different chambers so that the water quality is better controlled, right, from the bad quality to cleaner quality. And then it can effluent and then be introduced into the settling tank. Okay, and there are also channeled flocculators. We also call them as baffled channels, right? So for these baffled channels, they're also called hydraulic flocculators. So what happens is that if we look from the bottom, from the top to the bottom, then they're composed of different baffles here. So water have to go through these zigzag patterns, right? First go to the right and then go to left, right, left, right. So basically this is enhancing the residence time or increasing the retention time that's in this reactor here. And this is basically looking from the top to the bottom. And if we further look from left to right, you can see that for each of these baffles, they either exist above the, so basically they are either distance from the bottom or they're distant from the top. So this guarantees that the water, for example, when they first they're introduced into the chamber here, they'll first flow to the bottom. And if we look from the top, they'll flow to the bottom right? And then they're going to go back in this way, that way, this way. And then this will guarantee that the water will get further cleaned up or have a longer retention time in this reactor here. So let's look at a quick question. So compared to the coagulation, why the smaller g is needed for the flocculation? And this is because we want to prevent the breaking up of the flux, right? So for the A choice here, it's actually the reverse here. So we want to prevent the destabilize of the particle. We want to stabilize these particles, right? So here, so as you can see, the coagulation and flocculation can be separated into different reactors. And actually, we can also combine them into one type of reactor. And this is called the upflow solids contact clarifier. So what happens is that it actually combines all of these steps, for example, coagulation, flocculation, and clarification into one reactor. So if we look at the schematics, actually the influent is coming from this tube here. And then once they get into this conical shaped mixer here, at the top, we feed in these chemicals. So basically these are the coagulants. And then here are small baffles that rotate at very large speeds. So if by using this smaller baffles, we're creating a larger mixing rate or larger, basically a larger velocity gradient, right? For these smaller paddles, they also don't need a very large power to rotate them at a larger velocity there. So this will guarantee the rapid mixing of the treated water, of the polluted water or the water sources with these coagulants. And then you can see that this has a conical shape. By having this conical shape, we basically enlarges the surface area. So if we have a larger surface area, then the velocity will also reduce, right? So because of that, in this baffle here, they're going to rotate at a smaller speed. And at a smaller speed, this will enhance the flocculation so that you're not breaking up the particles while you are still guaranteeing that there is adequate mixing of the water there. So after they're being treated, so basically you're going to form these larger flux, and these larger flux can get further settled down to the bottom, and the cleaner water will just come up to the top. Okay? So basically it can be divided into zone A, B, and C. So in the zone A, we're having this rapid mixing. Zone B will enhance flocculation and solid contact. And zone C will be the upflow and sludge blanket zone. Okay. So after the water are treated, they will be transported to the effluent and then for further treatment process. So actually, if you look for pictures of the drinking water treatment plant, you can always or typically see these larger tanks or larger reactors with these circular shapes, right? So basically, these circular shaped reactors are these upflow solid contact clarifier, right? because it is very convenient to complete all of these clarification process with one single reactor here. So basically, this can also reduce the time for us to purify the water. Okay. So this is all about the coagulation, flocculation, and clarification. So next, we're going to talk about the softening process. And then, so basically, for the softening, we're trying to remove those larger metal ions from the water, right? So by definition, the softening, basically, you need to consider the uh, the the hardness of the water. And then, so basically, for the hardness, we have a total definition of total hardness. So the total hardness is basically the concentration of the ions that are able to form sedimentation when we heat them up. So they should include all of those ions that are able to form solids when they are heated up. So they not only include the calcium ions, right? So some ferric ions can also be counted as the hardness of the water. But because the calcium ion and magnesium ion concentration are so high there, so typically we just need to consider the calcium and magnesium ion in the water. Okay. So the total hardness is calculated by the calcium ion concentration added up to the magnesium ion concentration, and we will also use the equivalent concentration and typically convert that into the mass concentration equivalent as calcium carbonate. Okay, so last class we introduced how we can calculate these equivalent mass or equivalent concentration here. So for example, if we're talking about there are 40 milligram per liter of the calcium ion and also 40 milligram per liter of the magnesium ion. So in order to calculate the mass concentration as calcium carbonate, so basically first we need to calculate what is the equivalent concentration of the calcium, right? So for calcium, the Z value is equal to 2 because it can accept, so the salt here can accept 2 hydrogen ions, right? So if Z is equal to 2, then the way we calculate the the equivalent concentration is that we can use this mass concentration divided by the equivalent weight of the calcium, right? And the equivalent weight of the calcium is basically 40 divided by Z, which is 20 grams per equivalent, right? And then we can calculate what is the first, what is the equivalent concentration, and then we can convert it back into the equivalent mass concentration of the calcium carbonate, right? So the way we do that is we can divide 40 by 40 divided by 2, right? That is 20. And then we'll multiply that by the equivalent weight of calcium carbonate, which is 50, right? So this is going to give us 100 milligram per liter as calcium carbonate. And similarly, we can calculate what is the magnesium concentration in equivalent to calcium carbonate. So that can be calculated by 40 divided by 24 divided by 2, multiplied by 50. And we can calculate that. And then if we add it together, that's going to be the total hardness. Okay. And for the water, if the total hardness is between 60 and 100, they are considered as moderately hard. So the reason why we want to remove these hardness from the water is that they're going to form these sediments in the water. You may think that, oh, well, it might affect the how the water looks like, right? But if you can use some proper filtration, you can actually remove these sedimentations. But the more problem with these hardness is that once they form the sedimentation in the pipes that are transporting the water, then they're basically going to create these blocks, right? So that will reduce, so first, on one hand, reduce the surface area that's available, or cross-section area that's available for transporting the water. So there will be a higher water velocity. A higher water velocity means that there are going to be a higher pressure needed to transport water into different locations, right? And also, if we totally block the water pipes here, that's going to create leaks and more hazardous conditions. So that's why we always need to treat the hardness of the water. And since in Rolla, we're relying on groundwater as a drinkable water supply, we actually have to soften the water that's obtained from the groundwater in the deep wells. Okay, so that's all for the contents of this class. So next class, we're going to continue on the calculation of the hardness, and then we can further divide the hardness into different types. For example, the carbonate hardness and non-carbonate hardness. Okay, so we can do a quick review of the contents of this class, right? So what is the design criteria for the flocculation tank, right? Then if we consider about the velocity gradient, and why should we apply gentle mixing, okay? And we also, in the beginning, we talk about the coagulation, and then why should we use certain type of coagulants, and why do we need the rapid mixing after the coagulation, okay? So that's all for the contents of this class, and feel free to let me know if you have any questions. Thank you.